Okay, notes 2.7, velocity and other rates of change. So this is where we were starting to talk about this a little bit in note 6. Okay, so we said if we were given the standard function, and the standard function was given in a distance such as feet, and this is an object from a fixed point as a function of time t in seconds. So it says, well, what if we needed to find the derivative of that? Well, the derivative of the position function is just velocity. And let me fix that there because velocity, it didn't write it completely. Okay. It says describe how you would say this in real world terms. Well, we know that the derivative is also called instantaneous rate of change. So the velocity is the instantaneous rate of change in feet per second of an object at exactly t equals 4 seconds. Okay. Versus f prime of 4 equals 18 is telling us at t equals 4 seconds, the object has a velocity of 18 feet per second and that it is moving away from a fixed point at 18 feet per second. Okay. So in this example here, we're learning about the connection between the position function, velocity, and acceleration. So when we're given a position function, in order to find velocity, we take the derivative of that. So that's how I found this v of t function. And then from v of t, I can find acceleration, which is just the derivative of velocity. And that's how I got this. So when it says, how long will it take for the rock to reach a maximum height? Well, that is when we have velocity equal to 0. So I set this first derivative equal to 0 and get t is equal to 15 seconds at our maximum height. And then it says, how high did the rock go? Well, in order to see how high it went, that's when I look back at my position function. And I plug in the 15 seconds that I originally got, and then I get that the rock went up to 180 meters. Okay. I could also set this position function equal to 0 to tell me that it will take how many seconds to actually from start to finish. So when I throw the rock up until when it finally hits the ground. And when I set position function equal to 0, I find that is at time equals 30 seconds. Okay, more examples here. Another example here, but instead this is using rate of change. So like that f of b minus f of a over b minus a. Okay. This is talking about a position function s of t and how we can have a horizontal position or a vertical position. So a horizontal position are objects that can only move in a horizontal line. So for example, cars and people. Versus a vertical position of objects that can move in a vertical path. So that could be an elevator, rockets, and birds. Okay. Then we have instantaneous velocity. And instantaneous velocity tells us how fast something is going at the exact instance and in which direction. So when we take the derivative of the position function, we can write velocity in terms of the definition of the derivative. Okay, notice how that looks similar to f of x plus h minus f of x over h. Okay, we're able to define the motion of the object v of t based on what the velocity is looking like. So for example, if velocity is greater than 0, which means it's positive, we know that it's moving to the right if it's horizontal or going up if it's vertical. Versus if v of t is equal to 0, that means the velocity or the motion of the object is stopped. Okay, it's not moving left or right, it's not moving up or down. Okay. Then we have speed. Speed is the absolute value of velocity, because speed measures the rate at which the position changes. Okay. So With that being said, speed must be either positive or zero because we cannot have negative speed. Okay? We already mentioned that acceleration is the second derivative of the position function or the first derivative of velocity, and this is where we can determine the motion of the object depending on if acceleration is positive, negative, or zero. Okay. We can also indicate if something is speeding up or speeding down based off the sign of velocity and the sign of acceleration. So if the sign of velocity and the sign of acceleration are the same, no matter if it's positive or negative, we know it's increasing. If the sign of velocity and the sign of acceleration are opposite, then we know that the speed is decreasing. Something that I would memorize. Okay, something if you want to go over on your own. Velocity versus time and acceleration. Okay, how to read a graph. We don't do this too much. Typically, instead of reading a graph, we're going to look at a function, and they're going to ask you to actually find the derivative, which is velocity, and the second derivative, which is acceleration. But if you want to go through this and make sure you understand how to do these, okay, and notice that a lot of these problems are just kind of repeated, so I didn't go through all of them, okay. This is, again, talking about more of the definitions we already talked about, okay, so something good to just memorize and make sure you understand how to do. And, again, more definitions, more examples of everything we just did.